Hi everyone. In this video I'm going to talk about titrations. That's the whole purpose of the whole focus of this week. So what is a titration? Well, a titration is a lab technique to identify the molarity of an acid or a base. So for example, let's say you need to get a base, a sodium hydroxide, and you open up your bases cabinet and you see this. What's the problem? Notice the label tells you what it is, but not its molarity. And knowing the molarity is crucial. You know, is this a 12 molar sample? Is this a 0.01 molar sample? You need to know that. Or another example, what if you open your acids cabinet and see this? 0.200 molar HBr. Well, we have a label, but notice it's open on the top. Well, if it's open on the top, that means that for however many months that it's been sitting in there, we've been having water leave through evaporation. And only the water leaves. The HBr stays behind. This would be the H plus, which immediately turns into H3O plus, and Br minus. Those ions stay behind. So actually think about it. What happens to the molarity as evaporation occurs? It goes up. You learn this in the molarity FET. So if it's open like this, you can't trust this molarity anymore. We don't know what it is. So we can perform a titration to identify the molarity of an acid or a base. The basic idea is if you have a base you're trying to find the molarity of, you're going to add an acid to it. If you have, that's like this one. If you have a base, you're going to add an acid to it. If you have an acid that you're trying to find the molarity of, you're going to add a base to it. And here's the basics of how this works. No pun intended on basics. A titration is a lab technique to determine the molarity of an acid or base by measuring out a certain volume of the unknown sample. The unknown sample is what you're trying to analyze, so we call it an analyte. So for example, if you have this hydrobromic acid, if this is your unknown, then you would call this your analyte. And two, measuring exactly how much of a known molarity acid or base, which we call a titrant, needs to be added to it in order to neutralize the analyte. So the titrant is what you're going to add in a titration. That's your known. So for example, in this reaction, let's say I have my HBr. What I would do is find a sample of, well, let's say sodium hydroxide, NaOH, or any other base. If I know the molarity, like if I know this is 0.100 molar, I can add this to this, and I'll explain, of course, what you do, but basically you track the reaction, and this now acts as your titrant. This is your analyte, and you can figure out the unknown molarity of this. How do we actually do this? How do we know? Well, it says here you figure out how much of the known molarity acid or base needs to be added in order to neutralize the analyte. Remember, an analyte is either it's an unknown acid or an unknown base. A neutralization reaction is when you have some kind of acid, like in our example there, it's going to be, what's that, HBr? Yeah, so it's HBr, aqueous, plus KOH, is that what I added? All right, anyways, doesn't matter. Let's just pretend I did KOH, aqueous, yields. So the H bonds with the OH, giving us H2O, liquid water. The K bonds with the Br, giving us potassium bromide. That ends up being aqueous as well. And this is actually already balanced because you can think of this as HOH, and that can be written as HOH. So this is called a neutralization reaction. It's a double replacement when you have an acid and a base. And you always produce two things on this side. You produce water and you produce salt. Salt is any ionic compound that doesn't change pH. Technically, any ionic compound that's not an acid or a base is called a salt. So what you need to do is figure out exactly how much of the unknown, how much of the known needs to be added to the unknown in order to neutralize the analyte. What does that mean? Well, again, picture this HBr as our unknown, which we would call that the analyte, and picture the KOH as our known. What we need to know is at what point this HBr completely cancels out from the KOH with nothing left over. That's neutralization. Now, if you have a little cup of your acid and you add like 500 gallons of KOH, you will cancel your acid out easily. However, you're now going to have tons of extra base. That's not what we want. We need to know the exact point where the acid is perfectly canceled out by the base and nothing remains on this side. The only thing remaining would be water and salt. Well, how can we know when that's going to happen? Because there's no visual indicator of this. This looks like water. This looks like water. This looks like water. This is water. How are you actually going to know this? Well, the key is pH. When we track pH, we can know when neutralization happens. Let's say we start by tracking the pH of our HBr as we add KOH to it. What's the pH going to start as? High or low if it's in HBr? Well, HBr is an acid, so it's going to start with a low pH and it's going to start ticking up. Now, if you were to just dump 500 gallons of potassium hydroxide into it, your pH is going to end up being ridiculously high, probably close to 14, depending on the molarity of your KOH. That's not going to help us. We need to know exactly when these are canceling each other out. What's the pH going to be when these exactly cancel each other out? 7. Why 7? Because when there's none of this, and none of this, there's only water and salt. And what's the pH of water and salt? 7. So the basic idea is, how do we know exactly when neutralization occurs? We use an indicator that changes color at a known pH, or we use a pH probe. And basically, when pH equals 7, we know that neutralization has occurred. Now let's read what this says here. It says, this is called the equivalence point when neutralization occurs. It's the point when the reactants perfectly cancel each other out or neutralize each other. Now, just as a disclosure here, when we're dealing with a strong acid and a strong base, which is the most common form of titration, and it's the only one we focus on in Chem 1-2, equivalence occurs when pH is 7. If you go into higher levels of chemistry, you will learn that if you combine like a strong acid and a weak base, or a weak base and a strong acid, or a weak base and a weak acid, the equivalence point may not occur at pH of 7. But for the sake of this week, our equivalence is going to occur when pH is 7. So what that means is you track pH, you track pH, you track pH, it goes up, 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 and as soon as it hits 7, you stop, and you're done. Now, if this were switched, if your unknown was your KOH and you were adding your HBr to it, well, it would just be the opposite. Your pH would start high, and as you drip acid into it, it's going to get lower and lower and lower, and as soon as it hits 7, you're done. Let's go through an example. So you have a 22 milliliter sample of an unknown molarity potassium hydroxide. Unknown molarity, this is our analyte. It's the sample we're analyzing. And let's see what that would look like. So here's my potassium hydroxide, KOH. Okay. You titrate it using 0.200 molar hydrochloric acid. That's our known, which makes this my titrant. Now, what does that actually look like? Well, in the lab, you use something called a burette, which is a glass tube that's open at the top, and you fill it with generally you fill it with the titrant, although you can switch it and fill it with the analyte, it doesn't actually matter. And out of the bottom of this drips out your sample. Now there's a little stopper on there where you can control exactly how much you want to drip out. And this has lines where you actually track the volume that has ended up dripping out. This is called a burette. And one of the follow-up videos you're going to watch goes through the actual lab technique here. So the basic idea is you are going to add, in this case, your acid. So this is my, what's the acid here? Hydrochloric, HCl. You're adding your HCl to the KOH. It tells you how much acid was needed, it gives you the molarity of the acid, and it gives you the starting volume of your unknown potassium hydroxide. So to solve this problem, step 1, you want to write down all the relevant data you have and be specific about what solution it's for. Don't just say V equals 22.00 milliliters, because it's volume of what? There's 2 solutions here. Number 2, figure out the moles of the titrant, the one you know both the volume and molarity of, using this formula. Now this isn't a new formula. Remember, you learned molarity equals moles over liters. So if we just want to rearrange that to solve for moles, just move the liters up here and you end up getting this formula. Step 3, write the balanced equation, then use stoichiometry to convert the moles you just found of one into the moles of the other. So you see how stoichiometry is always at the middle of chemistry now. Step 4, you now know the volume and the moles of the analyte, or the unknown. So now you use the same molarity formula to find the unknown molarity. So let's go through this question. I copied the same question over here. So the first thing I'm going to do is just write down all the pieces of information it gives me. I call these the puzzle pieces. So we have 22.00 milliliters. Now, if we're going to be using that molarity formula, we're going to need these to be in liters. So I may as well convert them right away. So this is 0.02200 liters of unknown molarity potassium hydroxide, KOH. That's one puzzle piece. Next puzzle piece, I titrate it using this molarity hydrochloric acid. So 0.200 molar HCl. It takes 15.7 milliliters, or 0.0157 liters of the acid. What's the acid? Hydrochloric, HCl. Okay, so I have 3 puzzle pieces. I need to solve for the 4th, which is my molarity of the base. All right, at this point, I say, which of these do I know 2 things about? Well, I know 1 thing about the KOH, 2 things about this. So I know my molarity and my liters of the HCl. So you're going to use the formula molarity equals moles over liters, or moles equals molarity times liters, to find moles of the one that you know 2 pieces about. So the moles is going to be 0.200 molar, or I could say moles per liter for the sake of getting units to cancel. Liters is 0.0157 liters. Liter cancels liter. I'm left with moles, which makes sense. 0.200 times 0.0157 gives me 0.00314. My unit is moles, and moles of what? HCl. So that's how many moles of hydrochloric acid were present at that equivalence point. Now I'm going to use my balanced equation and use stoichiometry to convert the moles of HCl into my moles of base. So I have KOH, aqueous, plus HCl, aqueous, yields H2O, liquid, plus KCl, which is aqueous. If I think of this as HOH, it becomes very clear this is a 1:1:1:1:1 ratio. So if I have 1:1:1:1:1, so if I have 0.00314 moles of acid, how many moles of base do I need? Well, easy, same number, 0.00314 moles of KOH. So that's how many moles of KOH need to be present at that equivalence point. No more, no less. We're trying to find molarity of the base. So notice I now have my moles of KOH. Up here, I have my liters of KOH. Use those to find molarity. So remember, molarity equals moles over liters, which in this case equals 0.00314 moles divided by 0.02200 liters. Forgive my handwriting here. 0.00314 over 0.0220 gives me, with how many sig figs? I see 4, I see 3, I see 3. I want 3 sig figs. 0.143 molar. That's my answer. Let's do one more. So here I have a sample of hydroiodic acid, which is a strong acid. So that's my first puzzle piece. Well, actually, it's not a puzzle piece yet because I have no data. You decide to titrate it using 0.350 molar strontium hydroxide, strong base. You prepare a 12.0 milliliter, or 0.0120 liter sample of the acid. What's the acid? Hydroiodic HI, aqueous. The equivalence point is reached when 15.2 milliliters of the strontium hydroxide solution is added. So that's going to be 0.0152 liters of strontium hydroxide. Okay, so you might want to pause, try solving this on your own. Here we go. So I know two things about the strontium hydroxide, so I'm going to start there. I know molarity in liters. I'm going to multiply those together to find moles. So 0.350 moles per liter, that's molarity, times 0.0152 liters gives me 0.00532. Come on. Oh, come on. I'm rushing now and it's making it worse. 532 moles of strontium hydroxide. Okay. Now it's time for a balanced equation. Strontium hydroxide plus hydroiodic acid yields HOH is liquid water, strontium iodide, which ends up being aqueous, is my salt. We balance this. We have two iodides, so we need two iodides. You could think of this as HOH, meaning one front hydrogen, one hydroxide. Here I have two front hydrogens, so I need a 2 there. That gives me two front hydrogens and two hydroxides, which matches two hydroxides. So this is a 1 to 2 to 2 to 1 ratio. So notice I have 0.00532 moles of strontium hydroxide. The question is, how much HI must have been present for this to be perfect, for this to be perfectly neutralized? Well, it's a 1 to 2 ratio. So what am I going to do to this number? I'm going to double it. 0.00532 times 2 gives me 0.0106 moles of strontium hydroxide. Oh, no, HI. Because I'm going from strontium hydroxide to hydroiodic acid. All right, I'm looking for the molarity of the acid. I know my moles. I know my volume, 0.0120 liters. 0.0106 divided by 0.012 gives me, I'm running out of room here, I'll write my final answer in blue on the left side, 0.883 molar. That's my answer. 3 sig figs, 3 sig figs, 3 sig figs. Okay, now there is a shortcut that only works sometimes. That's why I didn't start by teaching it. This method works every time. And how long did this take? Like 3 or 4 minutes? Well, if you want a shortcut, here's a formula. Molarity of the acid times volume of the acid equals molarity of the base times volume of the base. But here's the thing. This only works when the acid and the base have the same coefficient in the balanced equation. In other words, when the number of H's on the acid matches the number of OH's on the base. Now there is a variation of this that works regardless, but I find it to be more confusing than it is helpful. Technically it's, you do NB here and NA there, where the NB is the coefficient in front of the base and the NA is a coefficient in front of the acid. If you want to look that up and use it, you're welcome to, but I'm going to choose not to teach that. Just in my years of going through this, I find that that is more confusing than it is helpful. But this formula is nice and useful if you know that you can use it. So looking at this example, could we use that shortcut here? Well, my base has 2 hydroxides, my acid has 1 hydrogen. So therefore, no, we would not be able to use that. And as you could see, we have a 1 to 2. We could not use that shortcut. So you would just use this method. Looking at this example, could we use the shortcut? Well, I have KOH, that's 1 hydroxide, and HCl is 1 hydrogen. Yes, I could use that shortcut for this one. So let's actually see if it works. Let me just clear some space. All right, so the formula is capital MA means molarity of the acid, VA means volume of the acid, equals molarity of the base times volume of the base. Now notice it's V, it doesn't have to be liters. You can actually keep this as milliliters as long as you're consistent. So we're looking to find molarity of the base, so we want to find MB. So we got to get VB out of here. Since these are multiplied, we divide by VB. Just to be clear, that A is like a subscript A, like this is really M times V equals M times V. It's not four things all multiplied. So VB goes away over here, and basically the molarity of the base is going to equal the molarity of the acid times the volume of the acid divided by the volume of the base, which is going to equal molarity of the acid is right here, 0.200 molar. Volume of the acid, 22 milliliters of potassium hydroxide, that's my base. Here it is, 15.7 milliliters of acid. Divide that by volume of the base, 22.00 milliliters. And remember, milliliters are fine as long as we have both of them here. So milliliters cancel, we're left with molar. So 0.200 times 15.7 divided by 22. Calculator tells me 0.143 molar, which you can see matches. Okay. Let me just quickly run through one last example using the shortcut. In fact, I encourage you to pause here, work through this one, and then check. So lithium hydroxide is LiOH. Nitric acid is HNO3. Can we use a shortcut here? Yes, because we have one hydroxide and one hydrogen. It's the same number. All right, so molarity of the acid times volume of the acid equals molarity of the base times volume of the base. What's the molarity of the acid is that we're trying to find here. So molarity of the acid, we got to get VA out of here, so that's going to go here. So all we got to do is plug these values in. All right, molarity of the base, 0.425 molar lithium hydroxide is my base. Volume of the base, right here, 17.2 milliliters. Make sure I'm doing this right. Yep. Volume of the acid is 42.0 milliliters. Milliliter cancels milliliter. 0.425 times 17.2 equals, divided by 42.0 equals 0.174 molar. There we go. Okay, good luck.